In this video, we are going to be introducing analysis of variance, ANOVA, which is just a hypothesis test to compare the means of more than two populations. If we only had two populations, we could use a t-test or a z-test. Now, to explain the terminology, let me use an example. Let's say that we have 500 patients, and we are going to, in this example, we have several diets, right? Let's call the diets A1, A2, A3, and A4. And we have several exercise plans, right? And let's say that we have B1, B2, and B3. We have 4 different diets, 3 exercise plans. And we are going to put our patients in different combinations of diet and exercise. So the diet is one of the variables that is going to have an effect on the variable that we are measuring. What is the variable that we are measuring? Let's say that we are measuring blood sugar. Okay. So if what we are interested in measuring is blood sugar, then this is going to be what we are going to call the response variable. And whose blood sugar are we going to be measuring? The patient's blood sugar. So the patients are our experimental units. Okay. And what are the variables that we believe will have an effect on the response variable, which is the blood sugar? The variables are the diet and the exercise plans that our patients will have. So the diet is a factor, and we are going to call this factor factor A. And the exercise plan is also a factor, and we are going to call this factor B. So in this experiment, we have 2 factors. One of them is the diet, the other one is the exercise plan. Now the diet, how many diets do we have? What are the values of this factor? A1, A2, A3, and A4. So this A1, A2, A3, and A4 are the levels of factor A. And B1, B2, and B3 are the levels of factor B. Levels of B. So if to a certain patient we are giving this diet A1 with this exercise plan B1, A1B1 is a treatment. That is the treatment that we are giving to a particular patient. That is a treatment. So this would be another treatment. If we give diet A3 with exercise plan B3, then that is another treatment. So what are treatments? Treatments are combinations of the levels of this factor with the levels of that factor. Okay. So let's say that as another example, let's say that we have another experiment with the same 500 patients, but we only have one factor, which is the diet, factor A. In this experiment, there is no factor B. Okay, there's only one factor, and we have A1, A2, A3, and A4. So if we only have one factor, what are the treatments now? The treatments before were combinations of these factor levels with these factor levels, but now we have only one factor. So this is going to be a treatment. This is another treatment, another treatment, and another treatment. So when you have only one factor, the treatments are simply the levels of the only factor that we have. Okay, so in your textbook you will have, whatever textbook you're using, you will probably have an explanation of all these terms. What is the response variable? That is the variable that we are interested in measuring. What are the experimental units? The people or subjects on which the response is measured. What are factors? Factors are variables that have an effect on the response variable, and factors will have different levels, right? When you analyze any question about this terminology, if you think that one particular variable is a factor and you cannot figure out what the levels are, then probably that's not a factor. Probably that is a level of some other variable. Let me see if I can give you an example. So let's say that we're doing a study to compare the effectiveness of two teaching methods, inductive and deductive. 100 students will be randomly assigned to one of the two teaching methods, and the SAT scores of all of them will be recorded. So, knowing this, what are the questions? The questions are first, what is the response variable? What did we say the response variable was? We said that the response variable is whatever we are trying to measure. So what are we measuring here? What we are measuring is the SAT scores. So the response variable is the SAT score. Now, what are the experimental units? And when you are going to answer this question, and you already know the response variable, ask yourself, whose SAT scores will be measured? And the answer is the SAT scores of the 100 students. So those are the experimental units, 100 students. These two questions are fairly straightforward, fairly obvious. 3. The next questions are probably a little bit more confusing. What are the factors? Do we have only one factor? Do we have more than one? What are they? And when asked that question, many students will say, we have two factors. One of the factors is the inductive method, and the other factor is the deductive method. Okay? Now, if you are one of those who thought that we have two factors, inductive and deductive, then ask yourself, if inductive is a factor, if inductor is a factor and deductive is a factor, then that means that this should have levels, and this should have levels also, right? So what are the levels of this factor? If you read this again, you will not be able to find any levels for inductive, because for this inductive method we didn't specify that we had this one and that one and that one. They just said inductive is one of the methods and deductive is the other method. So when you are answering questions like this and you cannot, and you thought that inductive was one of the factors and you cannot find the levels of this factor, then most likely that is not a factor. And this is not a factor. Most likely they are levels of another factor. So that was not the right answer. So in this case, we have only one factor. Only one factor, and the only one factor that we have is the teaching method. And the teaching method has two levels. One of them is inductive and the other one is the deductive method. Okay. And what are the treatments in this study? And we said before that if you have only one factor, remember what we did before? In this case, we had two factors, and the factor level combinations, these levels combined with these levels, gave us all these treatments in here. But we said if we only have one factor, the levels of that factor are the treatments. So in this case, we have only one factor, so the treatments are going to be the inductive and deductive. Okay, so now that we are more or less clear with the terminology, response variable, experimental units, factors, levels, treatments, then let's get into the first ANOVA design, which we will call the randomized, the completely randomized design. So remember that ANOVA is just the hypothesis test to compare the means of more than two populations. So like any hypothesis test, we will have the same steps that we did for all the previous videos. In step number 1, we must specify what HO and HA are, the null and the alternative hypothesis. So let's say that in our study, the number of treatments, let's say that we have the number of treatment is 4. That's what we're going to call K. So we're going to say mu sub 1 is equal to mu sub 2 is equal to mu sub 3 is equal to mu sub 4. The null hypothesis is going to be that there is no difference between all the treatment means. And the alternative hypothesis will be that at least two treatment means differ. 2 treatment means differ. Okay, so in step number 2, we are going to do the same thing as we did before, which is calculate the test statistic. And this is the tedious part of ANOVA, which is calculating the test statistic, because it will involve a whole bunch of summations. So the test statistic, we will call it F, and it is basically a fraction. The numerator of this fraction will be the variance between the treatments, and the denominator will be the variance within the samples. And to give you an example of what this is, what this really means, let's consider an example. I know that ANOVA is a hypothesis test to compare more than 2 treatment means, more than 2 populations. But for this example, let's say that we only have 2. Let's say that we have a group of boys and a group of girls. And let's say that we gave them some test, and we have the scores for the boys and the scores for the girls. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, and I'm going to represent the boys with a triangle and the girls with a circle. Okay, so let's say that we got here a boy with a 5, another boy with a 5, a boy with a 4, a boy with a 3, a boy with a 6, and a boy with a 7. And let's say that the score that we got for the girls was We have a girl with a 15, and another girl with a 15, and another one with 14, 13, and 16, and 17. Okay, so even if we don't know anything about ANOVA or about statistics, if we are presented with this situation and we are asked, would you conclude based on this that girls are smarter than boys? Well, based on these observations, I would say yes, because the difference between the means, or in other words, the variance between the means, is very large compared to the differences or the variance within the means, within the samples, the differences between this one and that one, this one and that one, and so on and so forth. So based on this, we couldn't really say that this difference between these means is due to sampling variability. This difference is too big because the sampling variability, we see that it is very little. So if we compute the variance between the treatments and the variance within the samples in a situation like this, we are going to find that the numerator is much bigger than the denominator, and maybe we're going to get something like 7.4, something like that. Okay, so based on this, we will say, well, yeah, I think that based on this, girls are smarter than boys. Now, what would be the third step? In the third step, we're going to find the rejection region. And the rejection region is basically going to help us decide how large this number must be for us to conclude that the null hypothesis is not true and that we must conclude the alternative hypothesis. So finding the rejection region will be determining how large this number must be. So for the rejection region, we are going to use the F distribution. And the F distribution is not like the normal distribution, is not like a bell. It looks something like this, skewed to the right. And the rejection region will be always to the right. The rejection region is going to be some region to the right. And this number here, which is a critical value, will be dependent on alpha and other two numbers, b1 and b2. What are they? Well, when we get into the details of how to calculate this fraction, we will see that the numerator has a certain number of degrees of freedom that we are going to call v1, and that the denominator has a certain number of degrees of freedom that we are going to call v2. Okay, so when we are going to find the rejection region will depend on alpha, the degrees of freedom of the numerator, and the degrees of freedom of the denominator. Your reaction right now may be probably, what the heck is he talking about? What is all of this? Well, you don't know what all of this is because I haven't explained it yet. But I want you to have a bird's eye view first of what ANOVA is. We're going to have to set it up, null and alternative. We're going to find the test statistic. That is the part that I'm telling you that is very tedious, and people normally don't do that by hand. That is done by software. Okay, and when I give you the details of how this is calculated, you will know what V1 is and what V2 is. But anyway, when you look at the table for the F distribution, immediately you notice, let me put it here, that now we have something called numerator degrees of freedom, which is what is called V1, and denominator degrees of freedom, which is what we are calling V2. Now, also, depending on which tables you're using, of course, but at least in my book, which is Statistics by McCabe, the F distribution is not only one table, it's more than one table. This first F distribution is for alpha equals 0.10. So there will be another one for 0.05, and there will be another one for 0.025, and there will be another one for 0.01, which are the most common values of alpha. So let's suppose that in our example we are using alpha equals 0.05, and just for the sake of argument, let's say that V1 was 7 and V2 was 12. So how are we going to find the critical value, which is the value that is going to determine what the rejection region is? If alpha is 0.05, V1 is 7, and V2 is 12, we go to the table. First of all, we make sure that we're looking at the right table, 0.05, and then V1 is 7. We said that V1 is 7 and V2 is 12. So if V1 is 7 and V2 is 12, then we get V1 is 7, V2 is 12, so we are right here, 2.91. Okay, 7 and 12. So the critical value is going to be 2.91. And then what is the rejection region? The rejection region will be the values of F that are greater than 2.91. Okay, and if the test statistic that we calculated here was in fact 7.4, then we see that 7.4 falls right in there, falls in the rejection region. Okay, our test statistic falls in the rejection region. So if that is the case, if the test statistic was in fact 7.4 and this was our rejection region, then we would make our decision in step number 4, and the decision is going to be to reject HO. We reject HO. Why? Because the test statistic falls in the rejection region. And if we reject HO, our conclusion is going to be something along these lines. You're going to say the data provide sufficient evidence to conclude at alpha equals 0.05 that at least 2 treatment means differ. Okay, treatment means differ. So, like I said, this is a bird's eye view of the whole process of ANOVA. What is ANOVA? It's a hypothesis test to compare the means of more than 2 populations. Step 1, in HO, you assume that all of them are equal. In step 2, at least 2 treatment means differ. So in step 2, we are going to calculate the test statistic. If this were our data, then of course we wouldn't have mu sub 1 equals mu sub 2 equals mu sub 3 equals mu sub 4. Of course, we would have only mu sub 1 and mu sub 2, because in this example, I only gave you two samples. Okay. And now, I don't know if we're going to have enough room in this video to calculate the test statistics. Otherwise, it will be in a second video. But we calculate the test statistic, we find the rejection region. If the test statistic falls in the rejection region, we reject HO and conclude HA. Let's see how long this video is already. Wow, it's already 24 minutes long. So this is the end of this video. So look for the next video where we will get into the calculation of the test statistic and finish off everything, and we will write our ANOVA summary table.